Okay, so going back to what we learned in Part B, where we learned how to derive our heat diffusion equation using cylindrical coordinates, we then took an example of a steady state problem with no energy generation and heat flowing only in the radial direction. We were then able to come up with a thermal resistance analogy, which is what we found here. So for the sake of this video, I'm going to change this height term here to a length, just because we're going to be talking about our heat transfer coefficient in a minute, and I don't want to get the two h's confused. So our equation now becomes the change in temperature, our driving force, which is equal to the heat flow Q multiplied by the natural log of our outer radius divided by our inner radius, divided by 2 pi times our length times our thermal conductivity. And as you can see here, this term is our thermal resistance. So to model this, I'm going to draw an example of a pipe. And we're going to say that we know the temperature along this surface. And to prevent heat loss, we are going to add insulation to both sides of this pipe. R1 is going to be the length of the middle of the pipe to the edge of the pipe. So that's going to be our inner radius. And our outer radius, R2, is going to be from the middle of the pipe to the edge of the insulation. The thickness of the insulation could be modeled as R2 minus R1. There's also going to be heat flow through here. There's going to be conductive heat loss from the pipe to the insulation. So that's going to be heat loss via conduction. And then from the insulation to the air, we're going to have heat loss via convection. And we know our thermal resistance term for heat loss by convection. As we saw in homework 1, that was 1 over our heat transfer coefficient multiplied by our area. Our area in this case is going to be 2 pi times our outer radius R2 multiplied by the length L. So plugging that in, we have 1 over our heat transfer coefficient H multiplied by 2 pi times our outer radius times the length. We can see that both of these thermal resistances are in series with one another. So the R total of this example is going to be the sum of our thermal resistance in convection, 1 over H times 2 pi R2L, plus this thermal resistance, the natural log of R2 divided by R1 divided by 2 pi times our length times our thermal conductivity. R1 is fixed, whereas R2 is dependent on the amount of insulation that we decide to add. So I'm going to take the derivative of R total with respect to R2. If I do that, we're going to find that this first term is going to be negative 1 over our heat transfer coefficient H multiplied by 2 pi times R2 squared times our length, plus R1 over R2 times 1 over R1 divided by 2 pi times our length times our thermal conductivity. Now, if we want to find an extrema, we are going to have to set this equal to 0. So to solve for R2, we can cancel our 2 pi L terms, and our R1s cancel as well. So we're going to be left with negative 1 over R2 squared times our heat transfer coefficient plus 1 over R2 times our thermal conductivity. So solving for this, we are going to find that R2 is equal to our thermal conductivity divided by our heat transfer coefficient. Therefore, we can say that the derivative of R total with respect to R2, evaluated at R2 is equal to K over H is equal to 0. Now we might be wondering, well, is this a minimum or a maximum? And in order to find that, we're going to have to take the second derivative. So let's rewrite out our first derivative. This was negative 1 over R2 squared times our heat transfer coefficient plus 1 over R2 times our thermal conductivity. And now we're going to take the second derivative of R total, still with respect to R2. And this becomes 2 over R2 cubed times our heat transfer coefficient minus 1 over R2 squared times our thermal conductivity. Now we can plug in our value for R2. We found that R2 is equal to our thermal conductivity divided by our heat transfer coefficient. So let's plug that in. We're going to have 2 over K over H cubed times H minus 1 over K over H squared times K. So we are going to manipulate this. We're going to have 2 over K cubed over H squared minus 1 over K cubed H squared. And we're going to find that this is 2H squared over K cubed minus H squared over K cubed. And this is equal to our heat transfer coefficient squared divided by our thermal conductivity cubed. And look at that, that is a positive number. That means that our first derivative is increasing, which means R2, our outer radius, is a minimum. So let's graph that and kind of understand what that means. So we're going to have R total on this side. This is going to be representative of R1, and this is going to be representative of R2. Now we know that R2 is a minimum, so we're going to have a parabola that is concave up. So it's going to look something like this. Now this point here is the minimum thickness of insulation. So anything beyond this point is going to increase our thermal resistance. Therefore, we can say that this R2 value we found is almost our worst case scenario. It's as if we were just using a bare pipe. We would need something beyond this point. But how do we figure out what this point is? Well, what we're going to do is we're going to take our original equation for R total, which is this guy right here. We're going to take that and we're going to drag that down. And we are going to now set this equal to 1 over our heat transfer coefficient H multiplied by 2 pi times R1 times our length. And here you would use some sort of graphing calculator to find a new value for R2, which is the maximum thickness of insulation we would need, and anything beyond that point is going to worsen our performance. Because the goal here, like if you're presenting this to an employer, you want to find the maximum amount of insulation you would need. That way you're using your money in a useful way. If you're adding too much insulation and you're performing even worse, you're just wasting money. So our goal was to find that maximum amount of thickness we have to improve our thermal resistance, but not worsen our performance. So if we were to use this, if we were to use this value for R2, that's our minimum. That's as if we're using a bare pipe. That means we're spending money to perform even worse. And we don't want to go too far beyond here, beyond this point, and spend a lot of money to perform worse as well. So that's why it's important to find this specific value of R2 to where we're at that perfect medium of spending enough money on insulation, but also having it perform the best.